folks. Welcome back to the chapter 2 or the next unit, which in this unit I want to talk about the linear programming. The linear programming does not mean that we are writing a computer program here. Programming is used in a very loose sense. What it means is an organized thought, an organized approach, or a rational approach. Linear is because of the relationship that exists within the model, meaning that there are several decision variables, parameters that are involved, which have a linear relationship among them. So that's what exactly it means. So in this lecture, I will briefly describe about what are the elements of linear programming and look at the graphical approach to those problems and also the computer methods. In my next lecture, I will solve a problem using the spreadsheet models. Okay, the learning objectives of this unit is, first, basically we had to understand what are the basic assumptions of a linear program. Let me just call LP from now onwards. Then we want to just take a graphical representation of how does this LP is represented. But before that, we got to get a mathematical relationship between those. And I want to tell you one thing, I am not expecting you to kind of develop these mathematical models and all. If you could do that, that's well and good. But our approach over here is using the Excel, the spreadsheet in the Excel, and that's where we'll be building the models straight away. Okay, but for initially, I will tell you how to do those things, but I may not require you to do those things. Okay, but what is important is in a regular setup, you have a spreadsheet in front of you, you got a situation in front of you, then you got to capture the situation in terms of the spreadsheet and now get the data, put the data, develop relationships and solve and come to a recommendation. So that's what it is in the real world. So my approach is going to be on very similar lines here. Okay. Then, so there are certain situations in which, we will have problems getting a solution, and what are those, like redundancy, infeasibility, and all. I'll touch on those later on. And, of course, the last one is the objective is to use the Excel spreadsheet and a particular tool that it has within it called Solver, how we use those to solve these problems. Okay. See, in a managerial world, you as a manager have several resources at your disposal, and you got to use those in an effective way. Why? The bottom line is profit. The profit is revenue minus the total cost. Revenue is quantity sold times the price that is charged. See, in the marketplace, you have some control over these two parameters, but not a whole lot. The price is dictated by the market, okay? But again, the quantity that you sell depends upon several different factors like quality and the market penetration and several different things that go into the mix over there. But what is definitely under your control is the total cost of that site, because it's under your control. So that's where the optimization and all that is important. And nowadays, in the present day world where the global competition is so severe, the world is totally flat. Okay, and so we have global trade going back and forth between these countries and all, and so you as a manager have to effectively use the resources. What are these resources? These resources are the labor hours, machine capacity, the funding that you have, the available time, warehouse space, and other raw materials that go into the process. Okay, they're all nothing but your resources. Okay, and using these resources, you want to produce products such as computers, automobiles, clothing, aircraft, train, any tangible product that you see and touch. Okay, or it can be intangible products such as services, meaning, for example, the UPS delivery package, so FedEx can get you within 16 hours. So how is it possible? And what are the operations that you need to do to make that happen? Or investment decisions, or market survey, health services, and or your tax preparation, many different things. Okay. Now these are the resource optimization is what we'll be looking at over here. And there are a lot of areas where this LP is effectively used. Sometimes we see it, sometimes many times we don't. But in your day-to-day life, you always experience that. For example, when you book the airline ticket and when you basically fly the airline segments from here to, let's say, San Diego, what is the best way to take you from here to there, keeping your airline purchase price to minimum? Okay, that is there. And secondly, when you come to work, you may pass the Coke trucks or or other or UPS or FedEx and all. So these people are either delivering packages or stocking up their the Coke products or the Frito-Lay chips and others at the convenience stores and all. What is the optimal route that they should take so that they can go take care of these things and get back? Okay, or when you plan a trip from point A to point B, you look at the map and you basically look for what is the shortest route. But nowadays on the net, you go to map.quest or maybe Google or any other, they say driving directions or the maps, and then you let it figure it out for you. What does it do? Again, it does exactly the same thing. What is the shortest route? These are some of the techniques that we'll come across in this in this course as we go along, and as you see it. It touches in your ways in many different ways. Like if you want to go to a bank, you want to get served, so you always join a line there. Again, that's part of this course. So, these are the personal experiences that you experience on a day-to-day basis. Along with it, I would also put on the blackboard the industrial applications. Okay, that you see where how this LP is effectively used. Okay, and all models that we look at LP in the development process, we first have the formulation. The next step is basically the solution. The third one is interpretation and application of that to the the problem that we are modeling. Okay. The basic assumptions is the conditions of certainty exist. What it means is, let's say that you are selling a product and that gets you $10 in profit for each unit. So that certainty says that you are going to get $10 in profit, no more, no less. Okay, if it takes 3 hours of machine time or carpentry time to finish a chair, let us say, it is going to take 3 hours, no more, no less. That's the certainty. That means you know a number and that is constant. That's not going to change. The proportionality means that if you basically take 3 hours to make a chair, for 2 chairs it's going to take 6 hours, for 3 it's going to be 9 hours, for 4 it's 12 hours. So it is proportional. And that's what the proportionality is, what lends to that linear term that we use in the program. Additivity means that if you basically spend 10 hours doing, let's say, on one activity and another 10 hours on the other activities, so together you spend 10 plus 10, 20 hours on these activities. That's that additivity. Divisibility means that the solutions need not be like whole numbers. For example, if you are producing chairs, it has to be a whole number, either 1, 2, 3, 4. It cannot be 1.5 or 1 3/4. It doesn't make a sense. Okay, but there are situations in which it does make sense for a continuous scale. Like for example, if you go, when you fill up your gasoline in your car, it's not going to be 1 liter or 1 gallon, 2 gallons, 3 gallons. It's going to be 2.33 gallons or 5.75 gallons. So that those numbers are continuous. That's that assumption 4 is divisibility. Okay. Now let's look at an example problem over here. This furniture company produces 2 products, tables and chair. Okay, each table requires 4 hours in carpentry and 2 hours of painting, and chair requires 3 hours in carpentry and 1 hour of painting. Of course, there are 240 hours available in carpentry and about 100 hours of painting time available. Now, due to the existing inventory of chairs, so the company doesn't want to produce more than 60 new chairs. Each table that is sold gets you $7 in profit, whereas each chair gets you $5 in profit. Now, the problem here is what is the best combination, that is in terms of the how many chairs and tables to produce to get the maximum profit. So decision variables are how many tables and how many chairs. So always call them by, like for example, T. Let T represent the number of tables to produce and C as number of chairs. Okay. So when you represent that, the first one is to maximize the profit, right? So each table gets you $7 in profit. If you produce T numbers, 7 times T, that's that first part that you see here. The 7 times T is the contribution from the tables. Each chair gets you $5 in profit. If you produce C number, then 5 times C is that contribution. So this is the total contribution. That's that additivity that we talked about. Now we simply can't keep on making tables and chairs because there is only finite resources available in carpentry as well as in painting. So that has to be figured in. Now let's look at the carpentry. How is the carpentry being used here? Each table takes 4 hours. So if you produce T numbers, 4 times T are the hours expended for producing T number of tables in carpentry. Each chair takes 3 hours. If you produce C number, 3 times C is the total hours expended in producing the chairs. So together, these are the number of hours that you use in making tables and chairs. That has to be less than or equal to 240 hours available. So you got to make sure that the units are consistent here. If you are using hours on the left side, right side also should be in hours. If you use minutes here, and they had to be in minutes here. Okay, apple to apple, oranges to oranges. Okay, that's the comparison basis. Now each table takes 2 hours in painting. T number takes 2 times T. Likewise, each test takes 1 hour. So if you produce C number, 1 time T is the number of hours that you use for chairs. Together, the total consumption of painting should be less than or equal to 100 hours available. So the number of chairs that you want to produce should be less than or equal to the 60 chairs. That's because of the inventory that you have. The last one basically says is non-negative. It is either you produce tables and chairs, in that case going to be positive number, or you don't produce, that is 0. They cannot be negative. Okay. Now this is a graphical solution for that. Now since we are looking at positive number for chairs and tables, they are in the first quadrant. So what you do is you first take this to be equal to and say that you are not producing any chairs. So how many tables can you produce just using this carpentry? That is 4 times T equals 240, or 240 by 4, that is 60 tables. So that's that 0.60 that you get. Now let's say that you don't produce any tables, just the chairs. So 3 times C equals 240, or 240 by 3, which is 80, is the number of chairs. Now add these 2 points. So that basically says that any combination that lies on this line exactly uses 240 hours, but it is less than or equal to. So that means any combination on the line and below. That's what that says. Now, just the same way that you did, for the carpentry, do the same thing for the painting. When this is 0, that is 2 times 50, that you get that 50 point right there. When this one is 0, you get C equal to 100, that is the other point that you get. So join those 2 lines. And again, any point lying on the line and below. But now you combine the earlier constant now. You need both painting and carpentry both. So that means only this area that's common to both is the feasible area. I refer to the video lecture also on this topic. Okay. So now any combination over here is going to have enough number of carpentry hours and assembly hours to make that combination. Okay. Now look at the other one is the C. That is number of chairs cannot be more than 60. So 60 or less. So the feasible region now for all 3 constraints is this truncated kind of a quadrilateral that you see here. Okay. Not exactly quadrilateral. 1, 2, 3, 4, 5. A pentagon. Okay. So by the corner point method, any corner point, that's where you have the maximum profit. Get the points, insert them, and find out, where you get the highest profit, and that is your optimal solution. Okay. Or on the other hand, you can look at the profit line, keep on taking it out until you hit the maximum point before you go into the infeasible area. So in this case, it is going to be tables equals 30, chairs equals 40. So that's the optimal solution. Optimal means that's best. There is no other solution that exists that gets you more profit than this combination. That's the optimal. Okay, so this is a graphical solution. Okay, that's a graphical solution. So, but what we will be using is, we'll be using the solver from this that's there in Excel spreadsheet. See, solver is based on a method called simplex method. There is a video lecture on that one that tells you basically how it happens. Now, the way that solver does is, it does the simplex method. Simplex method is a set of algebraic equations that you solve. Okay, so it takes one at a time, then finds out where the most profit is, then it stops right there. It doesn't have to go through all the corner points. First it establishes a direction based on some algebra, then goes to the next point, then tries to see is there any other point that's going to get you more profit. If not, then it stays right there and says this is where you get the most profit. So we will use this spreadsheet model to solve these problems. Okay, so what you want to do over there is have a column for each decision variable. T for tables, have a column for that. C for chairs, have a column for that. Number of units that you want to produce, always highlight that area. We will use the yellow color that says this is my decision and I have to make this decision. Okay, and when we solve this problem, the solver is going to place the answers in these cells. Now, what is the unit profit per chair? Per table is $7, per chair is $5. Now, the constraints: carpentry hours, each table takes 4 hours, and chair takes 3 hours in carpentry. Painting, each table takes 2 hours in painting, chair takes 1 hour in painting. Chair limit. Okay, now if you go back to the algebraic formulation that you saw before, you saw C less than or equal to 60. So right in front of the C, you did not see any number. When you don't see any number, the default value is 1. So that's that 1 that you see here. Now over here in this cell, that is in column D, what we want is, what is the total number of hours that we use? Okay, so here it is sum product, meaning that whatever the number of tables that are produced times 4 plus whatever the number of chairs that are produced times 3, add them up. So that means we are taking the product of these two numbers, that combination, then adding them up. So product and sum. So that's why the name is sum product. B8 through C8 and B5 through C5. These are the B8 through C8, B5 through C5. Okay, so that's basically gives us how many hours we would use with, once we know how many tables and chairs we will be producing. Okay, now look at for the painting. Painting again depends upon how many tables and chairs that you produce times the unit consumption rate. So that is the same sum product. Now look at the reference of the cells here. So this is common. So that is common for both that, this, and this, as well as for the profit. So that's why you see them prefixed with a $sign, meaning that this is an absolute reference. So what we'll do is, we will basically type in this formula at one place, then we'll just copy them down. We don't want to keep on typing for each one of them. So that's why we got to give them an absolute reference here, so that when we copy the formula, the cell reference is always drawn to these two and does not change. Okay, so the absolute reference is needed. We'll go back and look at the the tutorial that I have on referencing. Okay, so the total profit that you make then would depend upon the number of tables and chairs times the unit contribution. That's the sum product. That's what the objective function is. Okay, so now this is the left-hand side of the constraint that we saw. This is the right-hand side. This is the equality or inequality sign. We are going to adhere to this format when we solve the problems. When you use the solver, this is what the solution you get. The solver is going to put these numbers 30 and 40 when we solve the problem. In my next lecture, I will take a problem, then I will solve this. I will construct the spreadsheet, and then I will solve it. Then you take that as a reference and parallelly proceed on your own.